Okay, our second presentation for this session is a queuing model-based system for semiconductor production planning at IBM, Horst Disken, IBM Deutschland Research and Development.
Good morning, ladies and gentlemen. My name is Horst Disken from IBM. As mentioned, IBM in Germany. And I would like to, or we would like to, talk today about a queuing-based model we have developed over a certain period of time, which helps IBM to improve its lead time and capacity planning capabilities within IBM semiconductor manufacturing. Okay. Beside me, there are several co-authors. So it's Stephen Brown, IBM Industrial Engineering in East Fishkill, Ben Wheeler, former IBM Industrial Engineering and now fellow of the Leaders for Global Operations program at MIT, and others like Ingo and Thomas, which are not able to be here. And also we got a very strong management support by our senior management throughout this project. At a glance, today we want to introduce IBM's Enterprise Planning and Optimization System, shortly called EPOS. EPOS is based on new queuing theory models coupled innovatively with linear programming, and by doing so we have been able to enhance the applicability of queuing theory to such complex manufacturing lines like we have in semiconductor. EPOS is fully integrated as a software system, and by this the methods used by EPOS is fully integrated into our IT infrastructure within our factory, and by this also in the daily planning operations for our manufacturing line. And it has, since it was introduced a couple of years ago, has created tremendous value for IBM. What I want to cover in the next 30 minutes of this presentation, first of all, I want to introduce briefly semiconductor manufacturing at IBM. Then I would like to talk about the business requirements which have initiated this project. Then I would like to talk about the modeling approaches, I should better say, we have chosen here, which is quite a challenge to put this all together in those few minutes. Finally, Stephen will talk about the implementation of this system and the benefits IBM gained from it. Okay. Within IBM Semiconductor, we produce in Fishkill, we produce 300 so-called 300 millimeter wafers with the newest technology, and in our 40 billion facility in East Fishkill, we produce both regular manufacturing parts as well as development parts on a shared tool set, which introduces a special dimension of complexity, and we do this in a fully automated fashion. So we have a fully automated material handling system so that no operator has to touch the wafers. So, and where does those chips we produce go into? Where do the chips go into? First of all, we produce for our internal supply chain. That means we produce the processors for our server systems like System P and System C, as well as our supercomputers. But, and that may be more relevant for those in the room here which have children, we produce also the processors for the major gaming systems like PlayStation, Wii, and Xbox. So, what were the business requirements which have initiated that project? And therefore I have to go back to 2005, when we have started planning activities for a major factory expansion. And we were faced at this time with an increased complexity in our processes in terms of number of process steps we have to undergo and the number of involved tools. Furthermore, we had to ensure that we maintain competitive lead times and competitive productivity within this more and more complex environment. And considering the enormous cost of our machines, it's more or less obvious that we had to ensure that we use these machines in an optimal manner with respect to productivity, lead time, and utilization. So this forced us to revise our modeling approaches we have used up to this point in time, which were basically Excel sheet based, backed up by some discrete event simulation models. But due to the increasing complexity, it turned out that the discrete event simulation models became more and more time consuming to maintain and to run. So the run times became that long that it was impractical to use them in a daily planning business. So therefore, this yield to the following set of the 4 major requirements we had for the new modeling approach we looked for at this point in time. First of all, it was very important for us to combine capacity planning and lead time planning. The second requirement was to really build a model with a higher level of detail, and out of this we want to get a higher accuracy and in terms of covering the factory's performance, and finally to make the system really maintainable over years and not just a one shot. This has to really be integrated, fully integrated into the IT infrastructure of our factory. Okay, the modeling approaches. Before we go into the details of the modeling approaches, I would like to talk briefly about the modeling challenges within a semiconductor environment. Semiconductor manufacturing processes are one of the most complex manufacturing processes which exist actually, at least from my point of view. So there are several dimensions of complexity. First of all, the process flow is what we call the re-entrant process flow. We have this process flow consists of 800 plus different process steps. The machines on the shop floor have a high variability in terms of downtime, but also they produce a high variability for the process times too. Scrap and rework are important, as well as things like alternate routings and others. So, as I mentioned before, the discrete event simulation models turned out to be impractical because of the long run times. So the new approach we are looked for should be based on analytical methods. So we decided to go for a queuing theory-based approach. In order to do so, we first of all had to develop a general queuing server model which covers the characteristics of a semiconductor equipment. In the next step, we have to adopt this general model to the individual tools on the shop floor. In the third step, then, we have to model the material flow among those individual tools. And finally, we had to define the flow rates within this material flow, starting with the general queuing server model. The characteristic of semiconductor manufacturing processes is that at a tool, lots carrying up to 25 wafers arriving from different other tools at this tool. And there, at some tools then, or some machines, they get assembled to what we call the process batch. In these examples, we form it up to 50 wafers per batch, and then it gets transferred to the tool and processed there. So, from a queuing perspective, we had to develop a queuing system which covers lot arrivals, batch service, and we should, in order to keep it really general, we intended to allow generally distributed inter-arrival times and generally distributed service times. And we also have faced with a challenge that the lot sizes are not fixed, they are varying. So the lot size itself is also a random variable. So we have chosen a two-stage approach to model this. And by the way, we looked in the literature at this point in time, there was no model available which covers that all. So the first stage in this two-stage modeling approach is what we call the batching area, which reflects the batch forming process, and the second stage, the batch processing itself. Yeah. Okay, let's have a closer look to that. The batch forming process at the batching area causes a delay of arrivals at the service area. So what we had to do is we had to transform the inter-arrival stream of incoming lots into an inter-arrival stream of incoming batches at the service area. And we have been able to do this by an innovative application of limit theorems of renewal theory. And this ends up in a pretty nice and simple representation for the mean and the squared coefficient of inter-arrival times of incoming batches at the tool. So, having achieved this, we can consider the service area as an ordinary GGCQ, because we have incoming batches and batches get processed. The batching area, or the queue in front of the batching area, we approximate by an upper bound for wafers or lots awaiting batching, and the service area just approximated by known approximation formulas. So finally, this ends up in this approximation formula for this general type of queuing service for lot arrivals and batch service. So this was a general model, but now we have, of course, individual tools with different characteristics on the shop floor. So what we had to do in the second step was we had to adopt this general model to all the individual tools. Since we have more than 600 tools on the shop floor, you can imagine that we don't want to do this for each individual tool. So therefore, we have introduced a classification, what we call tool types. And we figured out that we have basically 4 different tool types on the shop floor. On top of that, we have splitted the service time of those tools into 2 parts. The first portion gives a fixed time, some setup conditioning time at the tool, and the second part we call the variable time, whereby the variable time depends on the number of wafers in the process batch. So based on data we collected in our manufacturing execution system, we have been able to determine the fixed time and the variable time for the different tools in those tool types, depending on the tool type itself and the process which runs on this tool. So as an example, I picked up here what we call the sequential tool. At the sequential tool, as said earlier, a lot arrives, and out of this lot, a wafer gets released into the process. The process itself in the tool is a set of sub-process steps. So, and then finally, all wafers get collected and released a slot again at the end. So how we modeled this? We modeled this as what we call in queuing theory a tandem queue, whereby the first queue of this tandem represents the capacity limiting bottleneck steps within the process. And so by this, the first queue represents the capacity of the tool. The second queue represents all remaining non-bottleneck steps, and by this it just represents the delay, because we introduced this as an infinite server system. Okay, so now we have models for the individual tools, but now the question is how do we model the material flow among them? So we have to connect them. And as already mentioned, material flow and semiconductor manufacturing is reentrant. So what does this mean? What that does mean, I would like to illustrate at this snapshot of our material flow. So these are the tools and the process flowing among the tools, and you see that the arrival process at one machine on the shop floor is not only triggered by the departures of upstream machines, it consists also of the departure streams of downstream tools. So what we had to do now, we have to model each of those tools as according our general queuing model. Yeah. And then in order to calculate now the queue lengths and by Little's rule then the queue time at each of these individual machines, we have to know two things. First of all, the service time behavior in form of the mean and the squared coefficient of variance. That's what we have determined in the second step from our data from the MES system, and we had to know the arrival time, the arrival patterns. And the arrival patterns is not an input because this is caused by the structure of a material flow and has to be calculated according to this structure of a material flow. How can we do this? First of all, obviously, we have to determine the departure process at each of those machines. In the second step, we have to split the departure because there might be different pathways through the network with the alternate routes. In the third step, we have to superpose different arrival streams because we could have different predecessors. And finally, arrivals take place as a lot and batch takes place as and service takes place as a batch. So we have to transform the lot arrivals into a batch service. And since this is a reentrant process flow, we cannot do this sequentially. We have to do that at once. Mathematically spoken, we have to create a set of equations, in this case a set of linear equations, to calculate the mean and the squared coefficient of variation for the inter-arrival times. And this was done in the following manner. First of all, we transform batch arrivals into batch departures. This is for the departure process determination. And the next step, batch departures get turned into batch arrivals by splitting and superpositioning. And in the third step, those arrivals, which take place as a lot, get transformed into batch arrivals by the transformation I have shown in the first step of the approximation. So by this we have an expression of lot arrivals as lot arrivals. This is basically the set of linear equations. We call this the traffic equations in queuing theory. And in formulas it looks like this, which ends up in a and if we solve this set of linear equations, we achieve the mean and the squared coefficient of inter-arrival times at each node in the queuing network. Having this achieved, we can now apply our general queuing model we have developed in the first step to calculate the queue length, and by Little's law we can derive from there the queuing time at each of the two. So this was now the model of a material flow itself. But this assumes somehow already a given routing matrix. In the last step we have to do is we have to define the flow rates through the network. Finally, we have to define the routing probabilities. And since we have alternate paths in the network, this is not trivial. This snapshot shows the multiple pathways for 3 products through 2 sequential steps in operation. And the question we have to answer now is how to set the probabilities each of these pathways will be chosen. Okay, skip it. How did we do this? We did this by introducing a linear program to set the routing probabilities for alternate tools. No. Okay, and and the objective function of this linear program has to reflect the behavior of a dispatching system on the shop floor, because the dispatching system finally determines the flow intensity through the fab. And the dispatching system tends to load balance the utilization of tools, of alternate tools. So first of all, the objective function has to minimize the sum of the mutual utilization differences in a set of alternate tools. But in order to really make this as productive as possible, or in our words, to really bring this load balance to the lowest possible level, we had to add another term, which is a weighted sum of the tool utilizations. And as formula, it looks like this. And you see at the second term in the sum this factor phi, which is basically the weight. And phi is given by phi is a penalty function, which is given by a stepwise linear and convex function. This function, by its shape, penalizes higher utilizations more than lower utilizations of the tools. And by this, it forces the optimizer, the solver, to look for balanced solutions on a lower level if possible. Okay, let me summarize what we call the major innovations. There are some others in modeling techniques we have used, but what we think are the major ones in the course of this project. First of all, we have developed a queuing system which allows batch lot arrivals and batch service with generally distributed service times and the arrival times given a random lot size. We have adopted this by a kind of tool type modeling to all the tools we have on the shop floor. We have introduced a decomposition method for material flows where the transportation takes place as lot and the service takes place as batch by enhancing existing decomposition methods. And finally, we introduced a linear programming to set the routing probabilities for this decomposition method. By this, we finally were able to model each tool and also the entire fab in terms of their performance indicators like queue length or work in process, queuing time, and capacity within one queuing model. And at this stage, I would like to hand over to Steve to talk about implementation and the gain benefits.
Thank you, Horst. I'm going to spend the rest of our presentation time describing for you some of the essential aspects of how we implemented the innovations that Horst just described, and then I'll conclude with a couple of examples of how this analytic solution has provided great value to IBM and our semiconductor manufacturing operations. As we mentioned at the onset, the factory in East Fishkill is highly automated and has a very advanced IT infrastructure. One of the benefits of that is that we record the actual processing times for every lot as it moves through every machine on its route. So we were able to create in the implementation of the EPOS system an automated extraction of that information, transformation of it into the formulations that Horst showed, and then a loading of that into the EPOS database. That information, once it's loaded, then becomes the foundation for executing the analytic model that Horst described. But as you, I'm sure, understand, past performance is not always a predictor of what we're going to do in the future. And so we also provide in the implementation of EPOS Java-based GUI for the users, primarily the industrial engineering users, to put sort of, if you will, up-to-the-minute information about processing times, new machines, new process flows into the model. With all of that information in place, we then execute on a regular basis. We update the EPOS model, and we produce predictions of lead times through the factory, utilizations of individual machines, and performance at each machine in each subsection of the factory. That information is used to present on a regular basis to management an outlook for how capacity is expected to be utilized in the factory, where bottlenecks are expected to occur. And in addition, we use that information for team-based activities across engineering, manufacturing engineering, development engineering, and industrial engineering teams that are responsible for managing and improving the performance of subsections of the factory. I want to emphasize as well, beyond the technical implementation, I want to emphasize that we're also very proud of how we have been able to succeed with EPOS in the sense that we have adopted it, and with its decision support capabilities, we've been able to enable a kind of a new organization culture. We've been able to change the organization. Horst mentioned at the onset that as I'm sure many of you know, one of the keys to success for projects of this nature is strong management support. We clearly had that, and that enabled part of this. But another important part was persistence and vision. In the course of developing the program and the methods that Horst described, there were always delays, or there were setbacks, there were complications, and I want to give great credit to the team members, particularly Ben, for his persistent vision that kept us on track and drove this through, and then executed the kind of education and the kind of articulation of the vision of where we were going across the organization, so that now we have fully embraced this. It's part of our ongoing business process. And to illustrate the value, I'd like to wrap up by showing a couple of examples of how we have used EPOS in East Fishkill. We mentioned again at the beginning that by 2005 we were facing a challenge of expanding the factory significantly. So one of the parts of that challenge is to determine how much investment we're going to make in new equipment and whether that particular investment is going to meet our lead time objectives. We've used EPOS recently to address this issue, and we're actually using it kind of up to the minute this week to as we begin to actually execute this expansion. How do we do that? Essentially, we represent future production schedules to the EPOS model. We execute the model, and we get a picture of bottleneck tools. Those bottleneck tools then become the seed or the foundation for a collaborative process that engages the development, manufacturing, and the industrial engineers in defining what the new tools in the factory expansion will look like. Very often, what we purchase and what we put into the new factory is not just replications of what exists in the factory, but rather new configurations and new processes. So we have to collaborate to define new tools that are then loaded into an updated EPOS model. It is run again. We are able at that point to assess the lead time contributions by machine type in the factory, and through a series of 2 or 3 iterations, we can then select. We can anticipate the effects on lead time from adding additional machines or removing additional machines, driving the overall investment down while still maintaining competitive lead time outlook. What has this meant to IBM? In particular, we have been able to devise a total investment scenario that, compared to prior methods, is about $30 million lower. We've decreased our space requirements by over 1,500 square feet, and we have done all of this while maintaining lead times within the strategic range that we desire. This kind of an approach was a foundation for the large investment commitment that the IBM Board of Directors made that gave us the go-ahead to do the expansion in East Fishkill, which we are currently in the midst of today. As a more tactical level, I'd like to conclude with an example of how we use EPOS to support continuous improvement efforts in the factory. As I mentioned a minute ago, EPOS predicts bottlenecks in advance, and it can be in the course of doing that, we're able to focus our improvement efforts and understand the value of particular strategies in improving anticipated bottlenecks in the factory. As an example, earlier this year, we used an EPOS model to anticipate that some new photolithography equipment, very expensive, very used frequently throughout the process, was going to be a bottleneck, and that information from EPOS in the form of operating curves showing trade-off between utilization and lead time was used to focus improvements on reducing rework, on reducing process times, and on reducing variability in repair times, which was kind of a new concept to some of the engineering members of this team. So what we got out of that in this particular case was a reduction in a significant portion of the factory's overall lead time by about 2/3. And as it turned out, we found that the performance was quite close to what was predicted by EPOS. So I'll conclude the presentation portion today with an extract from our letter of endorsement from our executive team. And I just want to emphasize in conclusion that EPOS has become a very valuable, unique, and valuable portion of the way we manage the factory in East Fishkill. And we'll, with that, open the floor to questions.
Can answer. The question was whether the routing probability decisions out of EPOS were then fed back into the material handling system in order to govern the dispatching decisions. No, it was completely separate. There is no link between EPOS and actual manufacturing decisions on the floor. It was a emulation of the way that the dispatching systems work in actuality on the floor. So the dispatching system will look at all the available run paths when a lot is to be dispatched to a machine and run at the nearest available machine that can run the process the fastest. So in optimizing the actual spread of routing probabilities, we look to try to balance the load in effect to emulate what would actually happen on the floor, and also to minimize the utilizations to sort of emulate running on the fastest machine possible, because we have several machines that run at different speeds. We didn't want to balance the load and have them all run on the slowest machines, because in actuality that's not what would happen. So that was the addition of the second term, which was to minimize and to penalize high utilization.
Maybe one comment, but there's somehow an influence of EPOS also to the dispatching system, but not a direct one, it's an indirect one. Because by EPOS we calculate the queuing time queue time distribution for the tools and what we call for the process types, which is a sequence of steps. And this is then used as a lead time target somehow in a kind of conwhip strategy to set lead time targets for the shop floor, and this lead time targets gets translated into lot priorities for the dispatching system. So that's the way how that feeds back. Twofold answer. I start with the first part and they take it. From a theoretical point of view, you have seen the two steps. We have the general queuing model, and we have the network decomposition. So what we did there, from a theoretical point of view, each of those queuing models we have validated against discrete event simulation runs, and we figured out that the that the accuracy is in a range of about 10%. So for both, for the single model as well as for the network. So we also have done some evaluations on the network part. But that was the theoretical piece, and now I guess Ben can talk about how we validated in the fab.
The validation in the fab was sort of a twofold approach. One was to validate the parameters that are input into the tool model, so the machine reliability statistics and the process time statistics and all that sort of attributes of the individual machines. That's updated monthly by the industrial engineering community, collect statistics from the factory and measure the actual performance versus what was input into the model. So that's one aspect of the validation. The second aspect of the validation is the actual output of the individual tool models as far as the expected utilization of the tools and the lead time of the tools. By nature of the queuing calculations, it's an average expected lead time and average expected utilization. So the way that we handled that was, like, in periods of stability for individual machines, we would look at the actual statistics of the machine. So for a given week, what was the average reliability pattern, what was the average process time, and the statistical distribution around that, and then validate the actual utilization and lead time around what the model would have predicted. So it's hard to do it on the fly because the nature of queuing modeling is that you're looking at a sort of an average and a distribution. So we would take an average, a longer period of time, look at the statistics of the machines during that period of time and validate it against the model.
I guess I'll add that that was not a one-time. I'll add that that was not a one-time event, but actually occurs on a regular schedule in the factory, and it's a part of the ongoing responsibility of the industrial engineer to ensure that the models are valid for his or her area.
Of course, the batch size is important for the solution, definitely. This was just an example with a 50 wafers. So that even increases the complexity. So we have some tools we have no batch sizes, so it's one. This was the cleaner example. It's 50 is a kind of industry standard. At furnaces, 100 is a kind of industry standard. And it's even, I hadn't had the time in the talk to talk about this, but it's even more complex. So we have to introduce what we call the effective batch size. So we are also, because sometimes you do not wait up until the batches get filled up to the maximum batch size. So we had introduced another method. So we are able to calculate based on the arrival rates what we call the most likely effective batch size for the tools. Because this is important, the batch size reduces capacity. And if you don't fill up the batches to the maximum, the reduced capacity, of course, increases the queuing time. So therefore we have for those tools where this is mandatory, we don't use the batch size, we use the calculated effective batch size based on the network structure and the product mix which goes into the network. Can you show me the alternate? Yeah, so we reflect in our model the different tool dedications, what we call it, so that some processes could take place. No, even further, the alternate routes. Once before. That's what I try to illustrate here. So that's exactly what it is. In this example, the lithography tool 2 can only process product C and product B, while product A, tool 1 only can produce product A, and both of tool 1 and 2 can produce product B. So these dependencies are fully integrated. So what we try to do with the objective function is to really think about what is the most productive way to put the load to the fastest tools, but sometimes they are only fast for a specific type of productions. So, and that exactly creates the problem and makes it non-trivial. Exactly this, and that's what we try to minimize this mutual use by the, let me call it a smart dispatch or assignment of workload to those tools to minimize the tool load.
Just to add on to that quickly, the linear program only would take into account the possible alternate tools, so you would just try to balance the load across the alternate tools. If there was enough load demanded on the lithography tools to drive the utilizations high to 90-95%, because that's the objective of how we want to run the factory, they would still be that high because there's nowhere else for the LP to push the load off onto the alternate tools. The value of EPOS that we, especially in lithography, have been able to get is that we can look at that high utilization and then also translate that into seeing what the expected lead time would be, because the lithography tools are very reentrant flow, added up over the entire length of the process, that adds up to a lot of cycle time. So we're able to sort of analyze the trade-off between the total amount of cycle time that one lithography tool or sector contributes to the overall product length, product lead time, and the level that we want to utilize the machines. Well, that's actually something that we talked about for future phases of EPOS. Because of the analytic nature of the model, it's possible to introduce optimization. If you put in cost of tools and you said, okay, I have $100 million to spend, what's the portfolio of tools that I can buy to reduce lead time the most that's the cheapest? It's not actually in the an LP model, but that's effectively what Steve and his team is doing with the iterative process and the capital investment scenarios. So that's the goal, is instead of just saying that the lithography utilization is high, well, let's go buy another tool. The benefit is we can say, okay, well, what are some cheaper other tools that if we buy them added up, they can save the amount of lead time that it would have to buy an expensive $100 million lithography tool.
And I guess I'll add that because we're working with an analytic model, we don't have the long run times associated with doing that kind of an analysis in a discrete event simulation, for example, so it is relatively straightforward and fast for us to evaluate alternative investment scenarios.